In the beginning, there was darkness, and then, bang, giving birth to an endless expanding existence of time, space, and matter. Now see further than we've ever imagined, beyond the limits of our existence, in a place we call the universe.
Each star you see twinkling in the night sky is a luminous sphere of superheated gas much larger than any planet. And each has a story to tell. A traumatic birth, a life on the edge.
Gravity collects the star in the first place, and then gravity wants to crush it.
And a death that rattles the heavens.
The whole thing goes off in a blinding flash. The biggest explosion in the universe.
The universe at its most volatile and action-packed. Life and death of a star. Like glittering cities in the desert, galaxies arise out of the great darkness of the universe. Galaxies made of billions of blazing lights called stars.
There are billions and billions of stars. In fact, in our galaxy, there are 400 billion stars just in our galaxy.
But how were these stars born? How will they die? And how can it be that all human beings on Earth owe their lives to the deaths of stars? The quest for answers begins here, in a cloud of dust and gas, hovering in the interstellar desert. You are looking at the pillars of creation.
The pillars of creation are a stellar nursery. New stars are in the process of being born in the central regions.
Located 7,000 light-years from Earth, the pillars are part of the Eagle Nebula, which is just one of billions of star-forming regions in the universe. The pillars are towering clouds of dust and hydrogen gas.
If you remember the periodic table of elements from chemistry class, you have the light elements up at the top, hydrogen, helium, lithium, this sort of thing, and then the really heavy ones as you get lower down.
It's hydrogen, the lightest, simplest, most abundant element in the universe, that is the key component of stars. Within a nebula, clumps of this gas and dust slowly coalesce into smaller clouds over millions of years, pulled together by a very familiar force.
The same force that connects us here to the Earth, that keeps us on the Earth, gravity, is the same force that pulls things together in a way that gives us planets and stars and galaxies in the universe.
Gravity, in many senses, is the most important force in astronomy. And when gravity acts in the universe, one of the basic things that it produces is stars. Stars are sort of the most basic unit of mass that is produced when gravity pulls mass together.
Each contracting cloud can produce anywhere from a few dozen to thousands of stars. To form a star like our sun, which is 1 million miles across, it takes a clump of gas and dust 100 times the size of our solar system. These clouds start off their lives bitterly cold, with temperatures hundreds of degrees below 0 Fahrenheit. But as gravity fragments and compresses them, the heat begins to soar. Within a few 100,000 years, the cloud spins into a flattened disk. Gravity coalesces the center of the disk into a sphere, where the heat rises to a scorching 2 million degrees. This glowing system is now known as a protostar. 10 million years later, the searing hydrogen core of the fledgling star soars past 18 million degrees, and something incredible happens. The core becomes so hot it can sustain thermonuclear fusion.
Thermonuclear fusion. It's a lot of syllables, but it just means it's hot there, and small atoms become big atoms.
Hydrogen atoms are moving fast enough that they actually will fuse together and will form a helium atom.
It's this nuclear reaction that produces the energy to power the star throughout its life, giving it a constant source of light and heat.
It's self-luminous, generates its own heat, and that's the essence of what makes a star a star.
If you've got fusion, you've got a star.
Once born, a star's life will be a constant battle, an all-out war against gravity.
Gravity collects the star in the first place, and then gravity wants to crush it. Gravity never gives up. Gravity wants to pull everything together. And so if the star is going to have a life, and a long life, it has to find a way to fight against gravity. You feel gravity all the time when you try to jump or you try to climb a rock. There's always gravity pulling you back down. And in order to fight against gravity, you have to have some way of applying a force which works in the opposite direction of gravity. So if there's a rope, you can use your muscles to pull on the rope and therefore resist and even overcome gravity. But that doesn't mean gravity gives up. Gravity is always working. And so you have to keep applying this force in order to not fall off. And if you give up or let go or the rope breaks, gravity immediately wins and you fall. The same kind of thing happens with stars. Stars are also trying to hold themselves up against gravitational collapse. Gravity wants to crush the star down to the middle.
For stars, nuclear fusion provides the rope in the form of pressure.
The heat gets all the particles in the star moving around quickly and they bang outwards, and that produces a pressure which can actually hold the star up against gravity. The amount of pressure pushing out on the star just matches the amount of gravity pulling in on the star, and it can sit there and burn happily until something changes.
A star will spend most of its life in this state of equilibrium. It's a phase scientists call the main sequence.
So our sun is in the main sequence. We're very happy it's in the main sequence. It provides us the same amount of energy almost every day. And that's what makes life possible.
All stars on the main sequence aren't alike. Some are much smaller and cooler than the sun. Others much larger and hotter.
So it turns out that how hot something is related to the color of the light that it emits. So a star like the sun, most of the light that comes out from the sun is sort of a yellow type color. If the sun were much hotter, the predominant wavelengths of light would come out into the blue or even into the ultraviolet. And cooler stars emit more red light.
Small, cool red stars like Proxima Centauri, the nearest star to the sun, are known as red dwarfs. They can be as little as 1/10 the mass of the sun, with surface temperatures thousands of degrees cooler. Red dwarfs are the most common type of stars in the universe.
There are many, many more of these sort of very dim red dwarfs floating out in space than there are stars like the sun. Now, of course, when you look in the night sky, you don't see the most common kinds of stars. You don't see these red dwarfs because they're so faint. You merely see the very rare, very bright stars that turn out to be very, very far away.
On the opposite end of the spectrum are the large blue main sequence stars. Averaging a surface temperature of 45,000 degrees Fahrenheit, they can be 20 times the mass of the sun and 10,000 times more luminous.